Okay, good afternoon or good morning for some of you. My name is Erica Podest, and I'm a scientist in the Earth Science Division at NASA's Jet Propulsion Laboratory, as well as an instructor for the NASA ARSET program. And this is the first of a four-part webinar series focused on Synthetic Aperture Radar, or SAR. And today I will start by covering the basics of SAR. So by the end of this presentation, you'll be able to understand the physics of SAR image formation, just the basic concepts, describe the interactions of SAR with the land surface, describe the necessary data pre-processing, and understand the information content in SAR images. So let's start with the electromagnetic spectrum, which is the range of electromagnetic energy that spans from very long wavelengths, such as radio waves, which can be the length of a football field, to very short wavelengths, such as gamma rays, which are the length of an atomic nucleus. So note that most of the energy on the spectrum is not visible to our eyes, and visible light is just a sliver of energy from the total amount that surrounds us. So I want you to think of this energy as waves propagating, not much different than waves crossing an ocean, except that electromagnetic radiation travels at the speed of light. So remote sensors are designed to operate at specific regions of the electromagnetic spectrum, according to their intended application. Microwave sensors operate within the range delineated in this figure, which is at a much lower frequency range than optical and infrared sensors. So to put things into context, the wavelength of light is about 300 to 700 nanometers, while for microwaves, it is on the order of 0.3 to 40 centimeters. And because of this huge disparity in wavelengths, the features on the Earth's surface appear differently in the microwave range than in the optical range. So there are advantages to observing the surface of the Earth within the microwave range, and it is primarily that microwaves are not hindered by day or night or most weather conditions as optical sensors are. So there are two main types of remote sensing observations, passive and active. Passive measures energy emitted or reflected by the Earth atmosphere system. So examples of passive sensors are optical and thermal. There are also passive microwave sensors, and they're called radiometers. They measure energy emitted from a medium in the microwave range. An active sensor provides its own illumination source, and examples of active sensors are LiDARs and radars, where a radar is analogous to an ultrasound. An instrument emits a burst of energy, and let's call that burst a signal, and that same instrument measures the portion of the signal that is reflected back. Active remote sensing in the microwave range is called radar remote sensing. In this webinar series, we will be focusing only on radar remote sensing, specifically synthetic aperture radar. So this slide lists in detail the advantages and disadvantages of radar remote sensing over optical remote sensing. The advantages of using radar, as mentioned in the previous slide, is that you can observe the surface of the Earth on either day or night conditions and under almost all types of weather conditions. Optical images are hindered by clouds or night conditions. Also, the radar signal can penetrate through the medium, meaning vegetation canopy, snowpack, or soil. And the extent of this penetration I will explain further along. Optical only sees the very top of the medium. In addition, with radar remote sensing, there are minimal to no atmospheric effects or corrections needed, as opposed to optical, where atmospheric corrections are critical for proper image interpretation. Finally, radar is very sensitive to the dielectric or electrical properties of the surface and to structure. So that's really important. Radar is sensitive to two things, the dielectric and structure. Of course, there are also disadvantages with radar, and that is that the information content in radar data is different than optical and sometimes difficult to interpret. Also for radar images, The presence of speckle, which is a salt and pepper, like a grainy type effect, makes it difficult to interpret the image. Finally, the presence of topography introduces distortions, which need to be accounted for, and all of this will be discussed further along. So this slide shows the advantage of having a sensor like radar that has the ability to observe the surface of the Earth regardless of cloud cover. The figure shows total fractional annual cloud cover averaged from 1983 through to 1990. And the colors indicate the percentage of time that there is cloud coverage. As you can see, some areas of the world are constantly covered by clouds, such as tropical regions. And it is areas like these that the radar is an ideal sensor. Here you can see an example of an optical versus a radar image. This is the Khrushchevskoye volcano in Kamchatka, Russia, which began to erupt on September 30th, 1994. So the image on the left is a photograph taken by astronauts on board the space shuttle during the early hours of the eruption, and clearly showing a thick ash plume. The image on the right is a radar image acquired during the eruption by SAR, which was one of the early synthetic aperture radars flown in space. And it was flown on the Space Shuttle Endeavour. So the red is L-band HH, green is L-band HV, and blue is C-band HV. So it's a false color composite. But on the radar image, you can clearly see the surface of the Earth despite the ash plume that was being emitted at the time. So now let's talk some of the basic concepts of radar. A radar is essentially a ranging or distance measuring device. And there are two categories of radars, imaging and non-imaging. So non-imaging is, for example, an altimeter. This webinar series is focused on imaging radars. And these radars are side-looking because if the radar would be looking straight down, such as the figure on the left, he would not be able to differentiate between 2 points, A and B. The figure shows that the signal will reach point A and point B at the same time and return to the sensor at the same time, which is why you wouldn't be able to differentiate them. However, if the radar is side-looking, such as the figure on the right, the time that it takes for the signal to reach point A and B is different, and therefore these 2 points can be resolved. So a radar consists fundamentally of a transmitter, a receiver, an antenna, and an electronic system to process and record the data. The transmitter generates successive short bursts or pulses of microwave at regular intervals, which are focused by the antenna into a beam. And the radar beam illuminates the surface obliquely at a right angle to the motion of the platform. The antenna receives a portion of the transmitted energy reflected, or it's also known as backscattered, from various objects within the illuminated beam. By measuring this time delay between the transmission of a pulse and the reception of the backscattered echo from different targets, their distance from the radar and therefore their location can be determined. As the sensor platform moves forward, recording and processing of the backscattered signals builds up a two-dimensional image of the surface. So I'm not going to get into the details of the physics of image formation, but in summary, the resolution of the radar in the along track, which is the azimuth direction, that is the direction that the sensor is moving, and the across track, also known as the range, is defined by independent parameters. The range or the across track resolution is dependent on the length of the pulse. The azimuth or the along track resolution is determined by the beam width, which is inversely proportional to the antenna length, also known as the aperture, which means that a longer antenna or a longer aperture will produce a narrower beam and a finer resolution. Since it is difficult to have long antennas in space, one can be synthesized by using the movement of the satellite or aircraft to simulate a very long antenna. Hence, it is called synthetic aperture radar, which allows for high-resolution images with comparatively small physical antennas. And through the use of signal processing of the Doppler shift associated with the motion of the aircraft. So radar pulses travel at the speed of light and can only measure the part of the signal that is reflected back towards the antenna. So most radars measure amplitude and phase, not all though, and amplitude is the strength of the reflected signal. Okay, so this amplitude is the backscatter coefficient, also known as sigma naught, which is the ratio of the fraction of the incident energy scattered back to the antenna per unit target area. And sigma naught is expressed in decibels by taking the log 10 of the energy ratio. This usually varies from minus 25 dB, which is an area where there's low backscatter or dark tones, because little energy is reflected back to the radar, to sometimes greater than 1 dB. Those are areas that have really high backscatter or bright tones, because a great amount of energy is reflected back to the radar. So a very important thing to remember about SAR is that the images contain information about two things, as mentioned earlier, structure and the dielectric properties of the land surface. There are radar parameters and surface parameters that influence the characteristics of the signal. And the next couple of charts will talk about three radar instrument parameters that influence the transmission characteristics of the signal. These are wavelength, polarization, and incidence angle. So wavelength is the length of the peak of one wave to the peak of the next wave. And in radar remote sensing, we often talk about wavelength rather than frequency. This is because the length of the wave defines the interaction of the signal with the surface or the medium. Wavelength is inversely related to frequency. It is the speed of light divided by frequency. The higher the frequency, the shorter the wavelength, and vice versa. The table on the right lists the common wavelength bands in radar. The letter codes, as you can see on the far left in the table, KAA, for example, L or P bands, were originally selected arbitrarily to ensure military security during the early stages of radar development, which is why these letter denominations are not in alphabetical order. And as you can see, each band has a wavelength and frequency range. So for example, when someone talks about a specific L-band radar, and I will give the example of one called SMAP, the Soil Moisture Active Passive Satellite. SMAP has a radar that operates at a specific frequency which within the L-band range. And in this case, it's 1.26 gigahertz. So something to note here is the variation in wavelength in Ka band, for example, which is on the order of 0.8 to 1 centimeters, and in P band, which is on the order of 30 to 100 centimeters. So it's quite a large range in wavelengths. And the tone on the SAR images are determined in part by whether there is signal interaction with the surface, which is determined by the wavelength. So there are two important things to remember about wavelength. The first is that the longer the wavelength, the greater the penetration through the medium. And the second is that the length of the wave will determine the interaction with surface objects. If an object or surface roughness is the approximate size of a wave, then there will be interaction. The surface will appear rough and there will be energy scattered back. If the wavelength is much smaller than an object, then there will be no or minimal interaction between the wavelength and the object, and the surface will appear smooth. There will be minimal to no energy scattered back. So for example, little radiation is backscattered from a surface with a height fluctuation on the order of 5 centimeters if L-band SAR is used, and the surface will appear dark. However, the same surface will appear bright due to increased backscattering if X-band SAR is used, which X-band is on the order of 2.4 to 3.8 centimeter wavelength, while L-band is on the order of 15 to 30 centimeter wavelength. So this table shows examples of applications most relevant to specific bands. If you're interested in forest-type studies where you want deep penetration through the canopy and information about forest structure, then you would go with something like L or P band. If you're looking at agricultural type studies where the biomass is not as large as that of a forest and you want penetration through the vegetation layer and information about crop structure such as leaves or stems, then you would go with C or X bands. For studies of ocean surface roughness, you would go with something like X or KU band. Okay, so this graph shows the extent of penetration through different mediums with different bands. In vegetated areas, X band will penetrate through the will partly penetrate through the canopy, very little, in fact, while C band can penetrate further, about halfway through the canopy, and L band can, in most cases, penetrate all the way and reach the soil. If you have a dry, bare soil, X band only sees the very top surface with minimal penetration, while L band can penetrate much deeper into the soil. In fact, there have been studies showing that in dry soils, L band can penetrate up to 1 meter, or sometimes even more. In the case of dry snow, X band sees only the top layer. It does have some level of penetration, while for L band, a dry snowpack will be just a transparent layer. Okay, so this is an example showing a comparison of optical and spaceborne images acquired in April 1994 for a region in southwest Libya where the soils are very dry. The image on the far left is a Landsat image, which is optical, and the images in the middle and right are from one of the early spaceborne SARs called SAR and XR, which I showed you earlier, examples of such, and they were flown on board the Space Shuttle Endeavour. And this was a demonstration mission to acquire SAR images and demonstrate their capabilities over given areas around the world. One of these early demonstration studies was in evaluating radar images for geomorphological studies. And this is an example of such. So SAR XR could operate in different bands. And here we have an example of an acquisition in C band, which is the image in the middle, and an acquisition in L band, which is the image on the right. And in this area, there are ancient drainage patterns cut in the bedrock that are not visible in the optical images because of sound cover. But most of the time, they appear as dark lines in the radar images. So the red arrows point to these fluvial systems. And since L band has greater penetration in these dry soils, sometimes on the order of, as I mentioned, 1 to even 2 meters, more of these drainage patterns or fluvial systems are discernible in L band than in C band. And from these early studies, the term radar rivers was coined for buried fluvial systems or paleochannels. So this is another example of radar penetration into soils. This area is part of the Nile River near the 4th Cataract in Sudan. Each image is about 50 to 19 kilometers. And the top image is a photograph taken with color infrared film from the Space Shuttle Columbia in November 1995. And the radar image at the bottom was acquired again with SAR XR in April 1994. It's a false color image using a combination of L and C band at different polarizations. The thick black band in the top right of the radar image is an ancient channel of the Nile that is now buried under layers of sand. And this channel cannot be seen in the photograph, and its existence was not known before this radar image was processed. So the area to the left in both images shows how the Nile is forced to flow through a set of fractures that causes the river to break up into smaller channels, suggesting that the Nile has only recently established this course. So this radar image has provided or allowed scientists to develop new theories to explain the origin of this great bend of the Nile in Sudan, where the river takes a broad turn to the southwest before resuming its northward course to the Mediterranean Sea. So this example is of penetration depth through vegetation. And the image on the top is a C-band image. Again, C-band has a wavelength of about 5 centimeters. And the image on the bottom is a P-band radar image. and P-band has a wavelength of about 40 centimeters. So note the difference, the greater details in the P-band image. The purple area, colored area in the C-band image is likely an area of low vegetation. However, the P-band image shows a lot more complexity in this area. Also, south of the low vegetated area is a forested area with lower biomass than the area immediately west of it. And also note there are purplish areas north of the river in the P-band image, which are areas having different forest structure or biomass. So you can see a lot more detail about the forest with the P-band rather than the C-band. This example shows radar signal penetration through vegetation to detect inundated areas. And this is an L-band SMAP radar mosaic of the Amazon basin acquired in April of 2015. In the middle of the image, you can see the Amazon River. And the further west you go, you can see vast, bright areas. And these bright areas is inundated vegetation. And L-band is ideal to detect inundated vegetation in the tropics because the signal can penetrate through most high biomass vegetation. And when I say inundated vegetation, that means there's vegetation and there's standing water underneath the vegetation. So another radar parameter, we've talked about wavelength. The other one is polarization, which refers to the plane of propagation of the electric field of the signal. Irrespective of wavelength, radar signals can be transmitted or received in different modes of polarization. So most radars are designed to transmit microwave radiation either horizontally polarized or vertically polarized. And this figure illustrates these planes of propagation. If you had a long string tied to an object, and if you stand at the very end of the string and move it up and down in a vertical manner, such as the figure in the very top, then the signal is vertically polarized. If you move the string horizontally from side to side, then the signal is horizontally polarized. And similarly, the antenna can receive either the horizontally or vertically polarized backscatter energy by applying specific filters. And some antennas can receive both. So there can be 4 combinations of both transmit and receive polarizations, which are as follows. HH for horizontally transmit and horizontally received, VV for vertically transmitted and vertically received, HV for horizontally transmitted and vertically received, and then VH for vertically transmitted and horizontally received. The first 2 polarization combinations are referred to as like polarized because the transmit and receive polarizations are the same. So HH and VV are like polarized. The last 2 combinations are referred to as cross-polarized because the transmit and receive polarizations are opposite of one another. Systems that collect data in all 4 combinations are called quad-pol, and they can more fully characterize structure on the surface. So in summary, polarization provides information on the horizontal and vertical components of the target. As part of this webinar series, there will be one webinar focused on polarimetric SAR, and that will be the 3rd lecture on June 5th by Dr. Nayara Pinto. So this is an example of a fully quad-pol L-band SAR system called UAV SAR, which is an airborne sensor. And in 2013, it acquired imagery over the Pacaya Samiria Natural Reserve in the Peruvian Amazon. This reserve is a vast wetland ecosystem, and the images on the top are mosaics of L-band, HH, HV, and BV. And the one on the top far right is the RGB combination of the 3. And this is an ideal way to visualize the contributions of different polarizations through their color combinations. The image on the bottom is a zoom subset of a part of the image and a case where you see the information content unique to each polarization, which in this case is representative of different types of wetland vegetations. So incidence angle is the angle between the direction of the incident wave and the Earth's surface plane. Large angles will be more sensitive to surface roughness and will penetrate less into the medium as opposed to small angles. Okay, so low incidence angles will result in high backscatter, and backscatter will decrease with increasing incidence angles. In general, the slopes facing towards the radar will have small local incidence angles, causing relatively strong backscattering to the sensor. And these areas will appear very bright, for example. So radar backscatter. We've talked about the radar parameters that influence backscatter, such as frequency, polarization, and incidence angle. And now we will discuss the ground parameters that influence backscatter. And these are dielectric and surface roughness or structure. So the brightness of features in a radar image is dependent on the portion of the transmitted energy that is returned back to the radar from targets on the surface. And the magnitude or intensity of this backscatter energy is dependent on how the radar energy interacts with the surface, which is a function of several variables or parameters. And these include the radar parameters, as well as surface dielectric and structure. So surface roughness is the dominant factor in determining the tones on a radar image. Surface roughness refers to the average height variations in the surface cover from a plane surface and is measured on the order of centimeters. So whether a surface appears rough or smooth to a radar depends on the wavelength and the incidence angle. A surface is considered smooth if the height variations are much smaller than the radar wavelength. So for a given surface, will appear rougher as the wavelength becomes shorter and smoother as the wavelength becomes longer. Rough surfaces will appear lighter in tone on an image, and size and orientation influences the interaction of the waves that are either horizontally or vertically polarized. The density of the scatterers will also influence the strength of the signal, making for a stronger signal when scatterers are closer together. And finally, the dielectric constant, which is an indicator of reflectivity and conductivity, determines in part the intensity of the returned signal. So let's talk about dielectric. The presence or absence of moisture drives the dielectric. So the complex dielectric constant is a measure of the electrical properties of surface materials. The dielectric property of a material influences its ability to absorb microwave energy and therefore critically affects the scattering of microwave energy. So dielectric is an indicator of reflectivity and conductivity, and the magnitude of radar backscatter is proportional to the dielectric constant of the surface. So for example, for dry, naturally occurring materials, their dielectric is on the range of 3 to 8. For liquid water, it is around 40 to 80, so it's frequency dependent. And therefore, the amount of moisture in the soil or vegetation can greatly influence an increase in reflectivity and radar reflectivity. Generally, reflectivity and image brightness increases with increased moisture content, which means that there is also less penetration through the medium. So for example, surfaces such as soil and vegetation cover will appear brighter when they are wet than when they are dry. The lower the dielectric constant, the more incident energy is absorbed and the darker the image will appear, or the object will appear on the image. This is an example of differences in image brightness for different landscape dielectric values. So the dielectric of frozen water is very low. It's on the order of 3.15 compared to liquid water, which is on around 80. In the northern high latitudes, when the land surface transitions from frozen to thawed in the spring, there is a very large change in dielectric, and consequently, a change in signal intensity from dark to bright. This example shows just that. This is a multi-temporal time series of an area near Fairbanks, Alaska, from the JRS-1 satellite, which was a Japanese satellite that carried an L-band SAR and flew in the 1990s. You can see that the February image, when the land surface was frozen, is darker in tone than the June image when the land surface was thawed. And in freeze-thaw studies, utilizing radar signals, dielectric is therefore the controlling mechanism causing changes in backscatter behavior. And it's really, radar is really ideal for these type of freeze-thaw studies in the northern high latitudes. So there are different types of backscattering mechanisms. And as a useful rule of thumb, the higher the backscattered intensity, the rougher the surface being imaged. So first of all, surface roughness refers to the average height variations in surface cover from a plane surface, measured in the order of centimeters. And whether a surface appears rough or smooth to radar depends on the wavelength and the incidence angle, as mentioned before. So it's considered smooth if the height variations are much smaller than the radar wavelength. The first type of backscattering mechanism is a smooth surface, also known as a specular reflection. So it's like a mirror, which is the top left image. A smooth surface acts like a mirror for the incident radar poles, and most of the incident radar energy is reflected away from the sensor, and those areas appear very dark. Open water surfaces tend to be specular reflectors. When the surface height variations begin to approach the size of the wavelength, then the surface will appear rough. And rough surface scattering is illustrated in the bottom left image. A rough surface will scatter the energy approximately equally in all directions or diffusely, and a portion of the energy will be backscattered to the radar. Then there is the opposite mechanism, which is called double bounce, and that's illustrated in the top right figure. When the two smooth surfaces form a right angle facing the radar beam, the beam bounces twice off the surfaces, and most of the radar energy is reflected back to the radar sensor. Double bounce is commonly seen in urban areas such as high-rise buildings, where you have these very geometrical angles. You have smooth surfaces like streets, and then you've got buildings. And you have energy being the radar energy being scattered from the street to the building and then back to the satellite. And then you find this type of double bounce as well in flooded areas where you've got standing water and then you've got upright standing vegetation, and this creates very geometrical angles and causing the energy to be, a large amount of the energy to be double bounced and scattered back to the satellite. That's why flooded areas appear very bright. So finally, there's volume scattering, which is illustrated in the lower right image. And volume scattering is the scattering of radar energy within a volume or a medium. And it usually consists of multiple bounces and reflections from different components within the volume. You can have volume scattering within a snowpack, for example, or within a vegetation layer. So this next slide is an example of volume scattering in a forest. And scattering may come from the leaf canopy at the top of the trees, the leaves on the branches further below, the tree trunks. And this figure illustrates all of the possible scattering mechanisms within a forest, including crown volume scattering, direct scattering from the tree trunks, direct scattering from the soil surface, trunk ground and ground trunk scattering, or crown ground or ground crown scattering. So these next couple of examples show the different scattering mechanisms discussed. And this example shows specular reflection. The image on the right is a mosaic of the Amazon basin from the SMAP radar, which you saw earlier. And this is an L-band radar. And the yellow circle delineates an area of specular reflection, which is open water and is part of the Amazon River. So flat surfaces such as paved roads, runways, or calm water normally appear as dark areas in radar images, especially at the longer wavelengths like L-band, since most of the incident radar energy is reflected away. Sometimes if you have a lot of wind that is causing a roughness on the water, you'll see a lighter tone, a dark, or a tone that is not as dark. So this is an example of rough surface scattering. And again, the area where there's rough surface scattering is delineated by the yellow circle in the SMAP radar image. And this is an area of very low to no vegetation, an area that has been deforested. Agricultural fields with low vegetation, tilled fields, savannas, bare fields, or in general areas that have low vegetation have rough surface scattering. And so the tone here is quite dark, but not as dark as a specular scatter. This example shows volume scattering delineated by the yellow circle on this map radar image, and this is a forested area. The intensity of volume scattering depends on physical properties of the volume. That would be variations in the dielectric constant and structure. And finally, this last example shows double bounce, delineated again by the yellow circle on this map radar image. And this is an inundated forest, meaning that the trees are in standing water. And the reason that it's so strong is because the signal bounces off the water, which is a specular reflector, onto the tree trunk or other components of the tree, and then back to the satellite. So we cannot measure the amount of standing water, but just that there is water above the surface. Whether it's 10 centimeters or a meter, that we don't know. And this is an example of the use of radar to detect oil spills on water. This example shows an image from the UAV SAR sensor, which is an airborne SAR sensor operating at L-band, fully polarimetric. It's an area in the Gulf Coast of the United States and was taken shortly after the Deepwater Horizon oil spill to determine the extent of the spill and movement of the spill onto the coastal areas through multiple image acquisitions. This is a false color image of HH, HV, and VV. The presence of oil smoothens out the sea surface and makes for an especially good specular reflector. So much smoother than the ocean surface where there's no oil. And here we can clearly see the oil extent as areas that are very dark in contrast to the ocean water, which appears as blue. This is an example of the use of radar for land cover classification. This example uses SAR images from the Japanese JRS-1 satellite, L-band SAR, operating in the 90s. Top left image is the radar image of an area near Manaus, Brazil, where there's a combination of forested and deforested land. The deforested areas have a darker tone, and as you can see, they also have some geometric features indicating that these are agricultural lands or grazing lands. And the image on the top right is a resulting classification delineating forest, regrowth, and non-forest. The bottom left is a different example. It shows part of a savanna region in the Amazon. And these savannas are characterized by short woody vegetation as well as non-woody savannas. So there's grassland or very short grasses. And you can see these different tones on the image, on the bottom left image. And the resulting classification showing that there is non-woody savanna, which are the darker tones, and areas where there's woody savanna are the slightly lighter tones. So there are a number of geometric and radiometric distortions that one has to correct for in radar images. And in this next section, we will discuss these distortions. So this slide, the side-looking nature of imaging radars results in certain geometric distortions. One of them is slant range, which is the distance of the signal between the sensor and the target. It is not the true horizontal distance along the Earth's surface. And this results in a varying image scale, moving from near to far and causing targets in the near range to appear compressed relative to the far range. So using trigonometry, ground range distance can be calculated from the slant range distance and platform altitude to convert to the proper ground range format. This figure shows a radar image in the slant range display, which is the top, where the fields on the road in the near range, so closer towards the sensor, on the left side appear compressed. And the same image converted to ground range display on the bottom shows these features in their proper geometric shape. So for most applications, it is desirable to have the radar image presented in a format which corrects for this distortion. to enable true distance measurements between features. And this requires the slant range image to be converted to ground range image. This can be done by the radar processor prior to creating an image or after data acquisition by applying a transformation to the slant range image. So similar to distortions encountered when using cameras and scanners, radar images are also subject to geometric distortions due to relief displacement. And this displacement occurs perpendicular to the flight path. And however, this displacement is reversed with targets being displaced towards instead of away from the sensor. So radar foreshortening and layover are two consequences which result from relief displacement. Layover occurs when the radar beam reaches the top of a tall feature, as seen on the image on the left. So this tall feature, the top is B, and the signal reaches the top before it reaches the base, which would be A. The return signal from the top of the feature will be received before the signal from the bottom. And as a result, the top of the feature is displaced towards the radar from its true position on the ground. And it lays over, that's why it's called layover. So it lays over the base of the feature. So layover is most severe for small incidence angles and at the near range of a swath and in mountainous areas. Foreshortening occurs, which is the image on the right, occurs when the radar beam reaches the base of a tall feature tilted towards the radar, so a mountain, for example, before it reaches the top. Because the radar measures distance in slant range, the slope from A to B will appear compressed, and the length of the slope will be represented incorrectly. Depending on the angle of the hillside or mountain slope in relation to the incidence angle of the radar beam, the severity of foreshortening will vary. Maximum foreshortening occurs when the radar beam is perpendicular to the slope. So this next figure shows the correction of foreshortening. And it's an image over an area of complex topography where there's foreshortening. And notice the bright slopes on the middle bottom of the image. They appear compressed compared to how they look after the image is corrected. So correction of the image is done utilizing a digital elevation model. This image is an example of shadowing. So radar shadow occurs when the radar beam is not able to illuminate the ground surface. Shadows occur behind vertical features or slopes with steep sides. And since the radar cannot illuminate the surface, there's no energy to be backscattered. And therefore, they're dark. And as incidence angle increases from near to far range, so will shadow effects, as the radar beam looks more and more obliquely at the surface. So the image on the right shows these shadow effects. And there are ways to correct for shadows through interpolation. However, I personally prefer to leave the shadow areas as they are, so I consider them data gaps rather than using interpolated values. So there are also radiometric distortions to account for. And a radar transmits more power in the mid-range portion of the illuminated swath than at the near and far ranges. And this is known as the antenna pattern. So the results are stronger in the center of the image rather than at the edges of the swath. So this antenna pattern can be corrected for. And it also varies dramatically as the range distance increases. So for a given surface, the strength of the return signal becomes smaller and smaller, moving further across the swath. And the antenna pattern correction can be applied to produce a uniform average brightness across the image swath to better facilitate not only visual interpretation, but actually data analysis of the image. So radiometric distortions also exist in connection with terrain relief, and sometimes they cannot be completely corrected. So the radiometric correction involves removing the misleading influence of topography on backscatter values. So for example, the correction eliminates bright backscatter caused by radar reflections from steep slopes, leaving only the backscatter that reveals the characteristics of the surface, such as what's related to vegetation and soil moisture. So in the image on the right, southern slopes are initially bright and northern slopes are dark. After correction, the southern slopes have a more uniform appearance. And however, some of the northern slopes stay dark, and this is attributed to different types of vegetation found in those areas, typical of vegetation found in northern slopes. This is a very important step in doing the radiometric distortion correction, and I will discuss these steps in webinar 2, where I talk about data processing and analysis. So the last part that I want to discuss is speckle. And speckle appears as a very grainy salt and pepper texture in an image. And it's caused by random constructive and destructive interference from multiple scattering returns within a pixel cell. Okay, as an example, a homogeneous target such as, let's say it's a grass field, without the effects of speckle would generally result in light-toned pixel values on an image, such as A on the right image. But reflections from individual blades of grass within each resolution cell results in some image pixels being brighter and some being darker than the average tone. That would be B, so that the field appears speckled. And a detailed analysis of radar images show that even for a single surface type, there are lots of gray level variations can occur between adjacent resolution cells. And these variations create this grainy texture characteristic of radar images. So speckle may make interpretation more difficult, and it's desirable to reduce speckle prior to interpretation and analysis. And speckle reduction can be achieved in 2 ways. One is multi-looking, and the other one is spatial filtering. So multi-look refers to the division of the radar beam into several narrower beams, in this case 5. And each sub-beam provides an independent look at the illuminated scene, as the name suggests. So each of these looks will also be subject to speckle, but by summing and averaging them together to form the final output image, the amount of speckle will be reduced. This comes at the expense of reducing the resolution. So it all depends on your specific application. If you want high resolution, then you want to apply less looks. If you don't care about averaging the original resolution to a coarser resolution, then you can apply a larger number of looks, of multi-looks. So the other way to reduce speckle is through spatial filtering. And this consists of moving a small window of a few pixels in dimension, and you can define the size of this window, 3 by 3, 5 by 5, 7 by 7. And you move this over each pixel in the image, applying a mathematical calculation using the pixel values under that window or within the window. And then you replace the central pixel with the new value. So the window is moved along in both the X and Y dimensions, 1 pixel at a time, until the entire image is covered. And by calculating the average of a small window around each pixel or a specific mathematical calculation, a smoothing effect is achieved and the visual appearance of speckle is reduced. So you can go with either multi-looking or spatial filtering, but again, both of these, they reduce speckle at the expense of resolution. So since they're applying, it's basically smoothing. They're smoothing the image. So the amount of speckle reduction desired must be balanced with the particular application the image is used for and the amount of detail required. So if you require fine detail and high resolution, then little or no multi-looking or spatial filtering should be done. If if you are looking at large areas for mapping or other applications over large areas, then speckle reduction techniques may be more appropriate and acceptable, where you do large-scale averaging, or you'd use larger multi-looking or larger windows for spatial filtering. So I personally prefer to do a multi-looking and just averaging. There are a number of different filters that are part of the software or embedded into different softwares that are available out there, and you can try how well they work. However, I've found personally that the best way to do analysis with radar images is just to do a simple averaging, which, because it's the minimal level of manipulation of the pixels. So the less you change the original pixel values, the better. So I want to keep as true to the original pixel value as possible. So finally, this is a table of different SAR sensors out there. There's RadarSat, there's Sentinel, there's RESAT, and the webinar 2 series will be focused on processing of data, SAR data using Sentinel, because it's a freely available data set, and it's currently operational. So it's a great resource, and we'll be using a software tool for analysis that is also freely available. So I encourage you, if you've seen this webinar series, to also look at the next webinar series on data processing. So this has specifics about each of these SAR sensors. And then if you're interested in SAR data collected in the past, you can have access to this data through the Alaska Satellite Facility. There are a number of different SAR data sets available, as seen here in this chart. The areas, the red boxes lists all of the different SAR data sets available, either satellite or airborne. So there's not only Sentinel-1, but there's radar from SMAP. There's a radar from CSAT, which was the first satellite L-band sensor in space. That was back in the 70s. If you want to go all the way back, it only flew for a couple of months. There's ALOS Pulsar, which is a Japanese satellite. It's L-band. There's some RadarSat data available, that's C-band. There is ERS from the European Space Agency, ERS-1 and 2, that's C-band. There's JRS-1. I showed some examples of JRS-1. This was a L-band SAR sensor from the Japanese satellite that was flown in the 90s. And then there's UAV SAR and Air SAR. These are airborne SAR sensors. UAV SAR is L-band, fully polarimetric, and Air SAR was a multi-frequency airborne SAR sensor. And then there are upcoming satellite missions, and there's a specific one that is called a NISAR. It is to be launched in 2021, and it's a joint satellite mission between NASA and the Indian Space Agency. It's going to have two SAR sensors. One is an L-band, and another one is an S-band. So the L-band will be made by NASA, and the S-band will be provided by the Indian Space Agency. It's going to be very, very exciting, very high resolution, and applicable to a number of different very important applications. Some of these are listed here, but very much targeting inundation, direction of inundation, change in water level in forested and urban areas, looking at flooding from runoff and snow melt, aquifer drawdown and recharge, oil and natural gas extraction from onshore fields, extensive degree of mine collapse. So lots of very exciting applications. All right, so that concludes this talk. But in summary, I know this is a lot of information. There are a lot of things to account for, but just remember that radar images provide information about dielectric, just the electrical properties of the land surface, and about structure. And then you have radar parameters, and then you've got land surface parameters. And most importantly for you to remember is what is the frequency, what is the wavelength of the sensor. And that will help you determine how well you can use it for your specific application. So with that, I conclude, and I'm open to your questions. Thank you very much.